Hello there, and welcome to the Sleepless Scientist, a quiet place in the cosmos where your thoughts can unwind and knowledge becomes a soft lullaby for the night. Tonight's journey will take us into one of the most mysterious frontiers of all, the edges of time itself. We'll travel with the James Webb Space Telescope, humanity's most sensitive eye, to peer into the faintest light ever seen, light so ancient it left its home long before our sun was even born. But before you settle in and get cozy, I'd love if you could take a moment to like this video and subscribe, only if you truly find these gentle explorations enjoyable. And when you're ready, leave a comment to let me know where in the world you're listening from and what time it is for you right now. It's always such a joy to imagine all of us scattered across the planet, sharing this same moment under the same ancient sky. Now, feel free to dim the lights. Maybe you have a warm drink beside you, or the faint hum of a fan in the background. Let your body sink a little deeper into wherever you are. The story we're about to explore moves slowly, like light through the dark, and it begins with a single question whispered by the universe itself. What if the first galaxies formed faster than time seemed to allow? If your thoughts start to wander tonight, that's perfectly fine. Just let them drift, like starlight finding its way across the ages. We'll still be here, quietly unfolding the story together. Imagine holding a mirror so vast, so perfectly curved, that it can catch the faint glow of the first dawn. That's what the James Webb Space Telescope does. It doesn't just look out into space, it looks back into history. Every photon it gathers has been travelling for billions of years, crossing a universe that has stretched and cooled and aged along the way. When those ancient waves of light finally touch Webb's golden mirrors, they tell us stories from a time when galaxies were barely learning how to exist. Light has a memory. The farther it travels, the more it stretches, its colour shifting toward red as space itself expands. Astronomers call that redshift, but you can think of it as a kind of cosmic aging. What was once brilliant blue starlight becomes a deep, invisible glow by the time it reaches us. The Webb telescope was built precisely to see that glow. The infrared whispers of the first stars. It works like a time machine, not by breaking the rules of physics, but by using patience. Imagine you're standing in a dark field at night. Far away, someone lights a candle. The farther that candle is, the fainter and redder it appears. Now picture a candle lit at the beginning of time, its flame stretched thin by the universe's breath. That's the light Webb is chasing. Since its first gaze in 2022, Webb has shown us things that almost feel impossible. In tiny patches of sky, smaller than a grain of sand held at arm's length, it has revealed hundreds of galaxies we never knew existed. Some of them come from a time only 300 million years after the Big Bang, when the universe was less than 3% of its current age. To our eyes, they look like smudges of light. But to astronomers, they are newborn cities in a universe that should still have been asleep. These galaxies are surprisingly bright. Too bright. They shine with the intensity of systems that should have taken billions of years to build, filled with stars, dust, and structure. It's as if, in the blink of cosmic time, the universe skipped the slow childhood we expected and leapt straight into adolescence. Some of these galaxies even hint at disks and bulges, organised shapes that shouldn't yet exist. It's like finding a fully formed spiral shell in an ocean that just cooled from lava. The data came first as whispers, deep field images from Webb's instruments called NIRCam and NIRSpec, sensitive enough to detect a few dozen photons from across the ages. Teams like JADES, SEARS and GLASS began analysing them, carefully measuring how much the light had stretched, how faint or sharp it appeared. And the numbers said something astonishing. Some of these galaxies sit at redshift about 13, maybe even 15, meaning their light left them when the universe was only a few 100 million years old. To give that a sense of scale, if the entire age of the universe were one calendar year, with the Big Bang at midnight on January 1st, and today at the stroke of the next New Year's Eve, these galaxies would have appeared in early January, long before galaxies like our Milky Way were even a thought in cosmic time. For decades, astronomers believed that the first galaxies grew slowly, gathering gas and dust under the gentle pull of gravity. But Webb's early glimpses showed brightness and order far beyond those predictions. It was as if someone had turned on the lights too soon. Of course, the telescope itself is a marvel worth dreaming about. Its mirror, 6.5 meters across, unfolds like a golden flower in the void. It orbits far beyond the moon, where Earth's warmth and reflection can't interfere. A place called the second Lagrange point, quietly balanced between sun and planet. There, shielded from heat by a massive silver sail, it listens to ancient light. Even the background of space is cold, about minus 230 degrees Celsius. Yet Webb operates with the delicacy of a watchmaker, adjusting its mirrors by nanometers, smaller than a strand of hair. Every image we see is a triumph of stillness. The universe expands, stars burn, galaxies collide. But this telescope simply waits, collecting the faintest signals until they become a picture. Each photograph is a memory from the beginning of everything, and within those memories lies a quiet tension. How can such complexity appear so early? Are we looking at galaxies that broke the timeline of creation, or are we simply seeing the universe's incredible efficiency, its instinct to build fast once conditions allowed? Maybe, like a child who learns to walk sooner than expected, the cosmos just surprised its parents. That's what makes the story of Webb so hauntingly beautiful. It's not that the telescope disproves what we know, it deepens the mystery. It shows us that even after centuries of staring at the sky, we're still standing at the shoreline of understanding, watching new waves of light roll in from a time before time. Somewhere, out there, the first stars are still shining, their light just now reaching us. And as we listen to those ancient photons hum softly against our detectors, we realise they've been travelling all this way just to say one simple thing. There was more happening in the beginning than we ever dreamed. If you could travel far enough into space, far enough that each step carried you backward in time, eventually you'd reach an era where no galaxies yet shimmered. Just darkness, drifting gas, and the faint echo of the Big Bang's first light. That was the cosmic dark age. For hundreds of millions of years after the universe began, it was a quiet ocean of hydrogen, waiting for the first stars to ignite. The James Webb Space Telescope, or JWST, was built precisely to find the moment when that darkness began to bloom. And when it finally turned its gaze to the deep sky, what it found made astronomers sit in silence. The telescope's first deep-field images were unlike anything ever seen. Imagine a tiny square of sky, so small you could cover it with the tip of your finger, filled not with emptiness, but with thousands of faint glimmers. Each one was an entire galaxy, glowing from billions of years ago. Some appeared red and soft like distant embers. Others, bluer and sharper, were closer in time. Together they formed a portrait of creation itself, a frozen frame of the universe just beginning to build. Among those glimmers were a few that stood out, brighter and more structured than anyone expected. They came from a time just 300 or 400 million years after the Big Bang. That's roughly when the universe was less than 3% of its current age. In cosmic terms, it was barely dawn. Yet there, unmistakably, were galaxies that looked as if they'd been forming stars for a long while. One of them was nicknamed JD's GS-Z390, a small galaxy observed in the James Webb Advanced Deep Extragalactic Survey, or JDES. Another, called Sears 99-456, was found in the Cosmic Evolution Early Release Science program. Both appeared at redshift around 13 to 14, meaning the light we see today began its journey roughly 13.5 billion years ago. To make that easier to picture, think of the universe as a single long day, from midnight to midnight. If the Big Bang happened at the first second after midnight, these galaxies would have formed by 1 a.m., long before the cosmic morning truly began. The surprise wasn't only that they existed, but how mature they seemed. Their light suggested dense clusters of stars, maybe even the faint beginnings of spiral structure. In a universe this young, astronomers had expected only small chaotic blobs, galaxies still gathering their material. Instead, Webb's images revealed systems bright enough to rival much later ones. It was like peering into a nursery and finding fully grown trees. At first, some thought there must be a mistake. Perhaps these galaxies weren't actually that far away. Maybe they were just dusty, older ones whose light had been reddened and dimmed by intervening clouds. To test that, scientists use one of Webb's most powerful tools, spectroscopy, the study of how light spreads into colour. When you pass a galaxy's light through a spectrograph, certain wavelengths are missing, absorbed by elements like hydrogen or oxygen. These gaps act like fingerprints, revealing both composition and distance. With Webb's instruments, those spectral lines confirmed what the imaging had hinted. The galaxies really were as far and as early as they seemed. That confirmation was stunning. For the first time, we were looking at structures formed less than 500 million years after time began. The Big Bang was still echoing. Space itself was still smoothing out from the turbulence of its birth. Yet here were billions of suns already burning, lighting up the young cosmos. Astronomers began to wonder, how could the universe have moved so quickly? Stars take time to form, to fuse hydrogen into heavier elements, to explode and enrich their surroundings. Dust and metals, the building blocks of planets and of us, come only after those first generations of stars have lived and died. But Webb was seeing evidence of dust, perhaps even heavy elements like carbon and oxygen, far sooner than expected. It's as if creation hit the fast-forward button. One of Webb's instruments, called NIRCam, peers through wavelengths invisible to human eyes, a deep crimson glow stretched by the expansion of space. In those tones, astronomers can trace the earlier starbursts, regions where gas collapsed under gravity to form stars at furious rates. The results suggested that these early galaxies were astonishingly efficient. Instead of taking hundreds of millions of years to grow, they may have converted their gas into stars within just a few tens of millions. That's roughly the difference between a slow sunrise and a sudden flash of lightning. Each of those galaxies was small by modern standards, perhaps only 1/10 the mass of the Milky Way, yet they radiated like miniature quasars. Their combined light may have helped end the cosmic dark ages, reionizing the universe and making it transparent once again. It's easy to forget how delicate this work is. The light Webb collects is unimaginably faint. Handful of photons captured after travelling for billions of years. In that journey, space itself has stretched by a factor of more than 10. The wavelength of each photon lengthened from ultraviolet into infrared, cooled by expansion until it could barely whisper its story. Yet the telescope's detectors, chilled to near absolute zero, can hear those whispers clearly. To study one of these galaxies is to read the universe's oldest diary. Every pixel is a memory, every shift in colour a note in a symphony written before there were even planets to hear it. And while the findings are still new, one truth is clear. The universe was a far more efficient artist than we ever imagined. It sculpted complexity at breathtaking speed, turning hydrogen and helium into light, dust, and shape with the elegance of a dancer. But in science, wonder always comes hand in hand with skepticism. For every astonished researcher, there's another double-checking calibration files, ensuring that what we're seeing isn't illusion. The community began reanalyzing the data, comparing methods, looking for biases or hidden lenses that might make distant objects appear brighter than they truly are. It's the quiet rhythm of science, excitement followed by humility, discovery followed by careful doubt. Whether all of these first candidates hold up under scrutiny, the pattern is unmistakable. Galaxies formed earlier, brighter, and faster than theory predicted. The cosmic timeline isn't broken, but it may be more compressed, as if the early universe, eager to express itself, skipped some of the pauses between notes. So, as Webb stares deeper into the past, what we're truly seeing is the universe learning how to make itself. Not slowly and hesitantly, but with a sudden burst of brilliance. And the light from that lesson is only now arriving, a faint reminder that the cosmos, for all its vastness, has always been restless, creative, and endlessly surprising. When astronomers first examined the galaxies Webb had uncovered, they didn't just see faint smudges of light. They saw weight. Not literal weight that could tip a scale, but the invisible gravity of countless suns packed together in those tiny glows. Every photon that left those galaxies carried a trace of how many stars were burning there, how dense the clusters had become. The brighter the light, the heavier the source behind it. And that's what puzzled everyone most. These early galaxies seemed too heavy for their age. In the standard story of the universe, gravity is patient. It gathers hydrogen and helium like a slow collector, pulling them into small clouds that merge, collide, and eventually ignite into the first stars. Those stars then group together, drawn by mutual gravity into the first primitive galaxies. It's a process expected to unfold gently, taking hundreds of millions of years to sculpt structures large enough to shine with the brightness of a modern galaxy. But Webb's images told a different story. The galaxies it found weren't small, scattered clusters. Some seemed to contain the mass of billions of suns already bound together, a cosmic weight that shouldn't have existed so soon. Imagine opening a history book to the first chapter and finding cities, skyscrapers, and glowing skylines already there. That's how these discoveries felt. To estimate a galaxy's mass, scientists look at its light, not just its brightness, but its colour, the balance of blue and red. Young hot stars shine blue, older cooler ones glow redder. By comparing the shades, astronomers can guess how many generations of stars have lived and died inside. And the verdict from Webb's data was staggering. Even at redshift around 13, when the universe was barely 300 million years old, some galaxies looked as if they had already built up more stellar mass than smaller galaxies near us today. That shouldn't be possible within the rhythm of standard cosmology. The model that guides modern astrophysics, known as the Lambda CDM framework, describes how cold, dark matter and dark energy shaped everything after the Big Bang. It predicts when and how galaxies should appear, how fast they can gather material, and what their maximum brightness should be at any point in cosmic time. According to that model, the early universe was still assembling its scaffolding, but Webb's galaxies seemed to have finished construction before the plans were drawn. Some researchers began calling them impossible galaxies. They weren't literally impossible, of course, but they strained the boundaries of our understanding. If their brightness truly reflected their mass, something fundamental was off. Either galaxies formed stars far more efficiently than expected, or our models underestimated how fast matter could collapse under gravity. It's worth pausing to picture what these early giants might have looked like up close. Their stars would have been blindingly bright, clustered so densely that the night sky within them might never have been dark. Enormous clouds of gas heated by newborn suns would ripple through them like slow lightning. There might have been no settled spiral arms yet, only turbulent shapes like smoke caught in a storm. But through all that chaos, gravity was already working as a sculptor, pulling everything inward, balancing creation and collapse in a fragile harmony. For scientists, this was both thrilling and humbling. Every data point was a whisper from a time when the universe was still experimenting with form. The weight of light, the measure of mass through luminosity, became a key to rethinking how galaxies were born. Yet, caution always shadows discovery. What if these galaxies weren't as massive as they seemed? Measuring mass through light is tricky business, especially across billions of years. Dust can make young galaxies appear older, reddening their glow. Certain emission lines can trick instruments into overestimating brightness. Even a small misreading in redshift can shift the inferred mass by orders of magnitude. Scientists knew this, and so the excitement of impossible galaxies came with a careful asterisk, if confirmed. That's the beauty of science, the balance between awe and skepticism. When Webb's first results were published, dozens of teams around the world began cross-checking them. Some used ground-based telescopes to follow up. Others relied on Webb's own spectroscopic instruments to refine measurements. Slowly, the picture began to settle. Some of the brightest candidates did turn out to be closer than first thought, but others, the most extraordinary one, held firm. Their light really had been travelling for more than 13 billion years. Their masses, even allowing for uncertainty, were undeniably impressive. So how could so much matter gather so fast? The answer may lie in the conditions of the early cosmos itself. Back then, gas was denser, cooler, and more evenly spread. Gravity didn't have to reach far to collect material. Once the first halos of dark matter began to form, invisible cocoons of mass that drew normal matter toward them, star formation could proceed explosively. Like sparks in dry tinder, each collapse triggered more. And because the early universe was small compared to its later self, those sparks ignited entire regions in a cosmic chain reaction. Another clue may come from the first generation of stars known as Population 3. They were enormous, dozens or even hundreds of times the mass of our Sun, and burned hot and fast. Their death seeded space with heavier elements, enriching the gas for later stars. If those giants formed in great numbers, they could have made galaxies appear older and heavier than they truly were, their brilliance mimicking maturity. Perhaps the early universe didn't need to cheat time after all. It just played the game with different rules: faster cooling, denser clouds, and stars that lived like comets, burning bright and vanishing in moments. Even so, Webb's discoveries invite a quiet philosophical question. We often imagine the universe as something that unfolds in neat stages, like chapters in a book. But maybe it's more like music, overlapping themes, rising and falling in tempo. The impossible galaxies might simply be the universe's first crescendo, a burst of creation so swift and full of energy that it left the score forever changed. When astronomers look at those faint points of light on Webb's images, they're not just measuring mass, they're feeling time bend in their hands, a sense that the universe, even in its infancy, already carried the ambition of everything that would follow. The galaxies might be ancient in light years, but their glow reaches us fresh, still warm with the memory of their making. And as we study them, we're reminded that the cosmos doesn't owe us simplicity. It only offers clues, each one a shimmer of truth hidden in the weight of light. If you step outside on a cold, clear night and look up, the light of the stars feels pure, clean, and eternal. But in truth, starlight is almost never untouched. It filters through something delicate and ancient, cosmic dust. The faint glow you see is shaped, dimmed, and softened by countless grains of matter drifting between the stars. It's in that dust, strange as it sounds, that the chemistry of life begins. So when the James Webb Space Telescope started detecting signs of dust and heavy elements in galaxies that existed barely a few 100 million years after the Big Bang, scientists paused. They expected light from that early age to be pristine, unpolluted hydrogen and helium. Instead, Webb revealed the unmistakable fingerprints of metals, carbon, oxygen, silicon, the quiet ashes of the first stars. It was as though the universe had gone from blank canvas to full palette almost overnight. To understand why that's so astonishing, we have to remember what dust really is. On Earth, the word calls to mind forgotten corners and sunlight through a window. But in space, dust is sacred. It's the residue of creation, fragments of stars that lived fast, died violently, and left behind the elements that make up everything solid, the calcium in our bones, the iron in our blood, the gold on a wedding ring. Dust is the universe recycling itself. But there's a rule, or there used to be. Before you can have dust, you must have stars that have already lived and died, and before that, you must have time. Millions of years for those stars to form, burn through their fuel, and explode as supernovae. Yet here, in galaxies like JD's G30, barely 300 million years after the beginning, Webb was finding the chemical fingerprints of several stellar generations. The timeline didn't seem to fit. The first stars, called Population 3, were unlike any we see today. They were massive, burning at tens of thousands of degrees, bright enough to briefly rival whole galaxies. They formed from pure hydrogen and helium, without any heavier elements to cool them, so they lived short, explosive lives, maybe only a few million years each. When they died, their cores collapsed and their outer layers burst outward, scattering the first metals into space. Those metals, what astronomers call heavy elements, meaning anything heavier than helium, cooled the surrounding gas clouds, helping new stars form more efficiently. That process is how the cosmic engine of recycling began. But Webb's data suggested that this cycle had already run not once, but several times by redshift around 13. It was as if the universe had gone from its first breath to complex chemistry almost instantly. Some spectra even hinted at the presence of dust grains large enough to absorb and scatter light. That's not just academic curiosity. It changes how galaxies look and evolve. Dust can shield young stars from harsh radiation, alter their colour, and shape the flow of gas that fuels new births. One possible explanation is that the early universe was simply faster at everything. In those compact galaxies, gas was dense and collisions frequent. Every time a star died, its debris didn't drift aimlessly for billions of years the way it might now. It quickly found its way into the next generation of stars. Imagine a cosmic forge where metals melted, cooled, and remade themselves in rapid succession. Each cycle added new ingredients to the mix: carbon, oxygen, silicon, transforming the chemistry of space before most of the universe even noticed it had begun. Another possibility is that the first stars were far more massive than we've ever imagined. The bigger the star, the shorter its life, but also the more material it can scatter when it dies. If the early universe was filled with titans, stars 100 times the mass of our Sun, they could have enriched their surroundings in a geological instant. Some may have collapsed into black holes, feeding the early seeds of the supermassive giants we find in later epochs. Others may have spread their heavy elements across their galaxies like pollen in the wind. The presence of dust so early also means that light from those galaxies carries a subtle disguise. Dust absorbs the blue part of starlight and re-emits it as redder, infrared light. That can make young galaxies appear older, because their colour mimics what astronomers expect from systems full of aging stars. Webb's ability to observe at infrared wavelengths helps disentangle that illusion. It lets us see both the absorbed and re-emitted light, tracing where dust hides and how it changes the picture. In one sense, this is exactly why Webb exists, to reveal the hidden half of the cosmos. Where Hubble saw sharp blue pinpoints, Webb sees the gentle red glow beneath. Through its eyes, astronomers realize that the early universe wasn't a sterile void, but already a complex ecosystem: stars, gas, dust, and the faint hint of molecules. Complexity didn't creep in gradually, it rushed in, as if creation was impatient to decorate itself. That impatience carries philosophical weight too. For generations, cosmologists assumed the early universe was simple, waiting to evolve into complexity. But Webb's findings suggest the opposite, that complexity bloomed the moment it was possible, as though the laws of physics themselves were tuned not just for stability, but for creativity. The cosmos didn't idle after the Big Bang. It got to work immediately, building the ingredients for everything to come. Still, as with all discoveries, humility is essential. Some of these early metallic signatures could yet prove deceptive. Strong emission lines, bright features in a spectrum caused by ionized gas, can mimic the appearance of metals or dust even when none is there. It's also possible that gravitational lensing, the bending of light by intervening mass, magnifies distant galaxies and makes them appear more evolved than they truly are. Webb's own spectroscopic instruments, like NIRSpec, are helping to confirm which signals are genuine and which are tricks of perspective. Even with those cautions, the picture is breathtaking. A universe only a few 100 million years old, already rich with the ashes of its first stars, already filled with the seeds of future planets, future chemistry, future life. It means that by the time our Milky Way began to form, the cosmos was already dusted with the remnants of thousands of earlier suns. The atoms that would one day become us had already begun their long journey, carried from explosion to explosion across time. When we look at those ancient galaxies through Webb's golden mirrors, we're seeing the moment when the universe first learned to recycle itself. Every grain of dust floating in those images is a relic of creation's first heartbeat, the same dust that, in time, would drift together to form worlds, oceans, and the breath we draw. So the chemistry of speed isn't just about how quickly stars lived and died. It's a reminder that the universe has always known how to turn endings into beginnings. In those faint, distant galaxies, the story of life itself was already being written. One atom, one spark, one quiet heartbeat of light at a time. In science, even the most beautiful theories occasionally tremble under the weight of new light. The discoveries made by the James Webb Space Telescope did not simply add details to the story of the early universe, they quietly questioned the tempo of the song itself. For decades, astronomers have relied on what's known as the Standard Cosmological Model, often called the Lambda CDM framework. It's not a single equation, but a tapestry of ideas, weaving together dark matter, dark energy, and the afterglow of the Big Bang. This model has explained with astonishing precision how galaxies form, how cosmic structures grow, and how the universe expands. It is the rhythm that underlies almost everything we know about the cosmos. But like any rhythm, it assumes a certain pace. In that model, the universe begins hot and dense, filled with nearly uniform gas. As it expands, gravity gathers the gas into small clumps, tiny halos of dark matter that act like invisible seeds. Over hundreds of millions of years, these halos merge and grow, pulling in more material, slowly forming the first stars and eventually the first galaxies. It's a patient process, elegant and slow. But Webb's images suggested a universe that was anything but patient. Galaxies seem to appear in large numbers only a few 100 million years after the beginning. Some were so luminous that, if their light truly comes from vast populations of stars, they must have accumulated, mass at a breathtaking rate. The early cosmos, according to these findings, was not a calm nursery. It was a bustling city under construction, with cranes already lifting steel before the foundation was dry. This is where the standard model begins to frown in confusion. The equations that describe structure formation, the balance between gravity pulling matter together and cosmic expansion pushing it apart, set a kind of cosmic speed limit. Within that limit, there's only so much mass that can gather in a given time. Yet Webb's galaxies seem to exceed it. They weren't supposed to exist yet, not in such numbers, not with such brightness. It would be easy to leap to the conclusion that the model is wrong, but science rarely works in such leaps. More often, it refines. Perhaps the rules still hold, but we've misunderstood how efficiently the universe plays within them. Maybe star formation was simply more aggressive in the beginning. To imagine this, think of the early universe as a field after a thunderstorm, wet, fertile, and full of potential. Dark matter provided the hills and valleys, the gravitational landscape. gas flowed into the valleys, cooled rapidly, and collapsed into stars. In today's galaxies, much of that gas is heated by radiation and explosions, which slow the process. But back then, the cosmos was simpler, its chemistry still clean. It might have been able to form stars at a rate 10 times higher than what we see now. Even so, there's a deeper challenge. If those early galaxies truly contained billions of solar masses in stars, then their dark matter halos must have been enormous, larger than any model predicts should exist at that time. To build such halos, small ones would need to merge in a rapid cascade, collapsing faster than expected. But gravitational collapse takes time, and time was short. It's like trying to grow a forest from seedlings in a single season. The soil may be perfect, but the calendar is uncooperative. Some cosmologists have suggested that perhaps the earliest density fluctuations, the tiny ripples in matter left over from the Big Bang, were a bit stronger than we thought. These ripples were mapped with exquisite precision by the Planck satellite, which measured the cosmic microwave background, the faint afterglow of the early universe. But those measurements reflect averages over vast regions of space. It's possible that in some smaller patches, the fluctuations were locally amplified, allowing matter to clump together earlier and faster. That wouldn't require rewriting the laws of physics, just adjusting the initial conditions. Others look to dark matter itself. In the standard picture, dark matter is cold, meaning it moves slowly and clumps easily. But if a small fraction were warm, with slightly faster moving particles, it could alter the timing of halo formation, creating more early seeds for galaxies to grow inside. These aren't radical departures from the model. They're gentle adjustments, ways of asking, what if the universe's ingredients were mixed just a little differently? And then there's the human element, the way our expectations shape what we see. For years, cosmologists believed that complexity takes time, that order is something the universe grows into gradually. It's a comforting idea. It mirrors our own experience of life. But the cosmos may not share our sense of pacing. The first stars and galaxies might have ignited with astonishing efficiency simply because the conditions were perfect. Dense gas, powerful gravity, and a universe still compact enough for light to echo from one end to the other in relatively short spans. It's possible that the impossible galaxies aren't impossible at all. They might just be nature showing off, demonstrating that creation, once begun, wastes no time. Still, the tension remains. If future observations continue to confirm large, massive, and chemically enriched galaxies at these early times, we'll need more than small tweaks. It could mean that our understanding of how matter behaves on cosmic scales requires a new layer, a rethinking of how dark matter interacts, or how the expansion of space unfolded in its first billion years. That thought isn't frightening, it's exhilarating. Every major leap in physics began with a small mismatch between theory and observation. The orbit of Mercury didn't quite fit Newton's laws. It led to Einstein's relativity. The faint ultraviolet glow of hot objects didn't fit classical physics. It led to quantum mechanics. Perhaps Webb's galaxies will be our next reminder that even the grandest model is still just a map, not the territory itself. When we look at those early lights, we aren't seeing the failure of the standard model. We're seeing its limits, the edges of its usefulness. Beyond that edge lies new terrain, still unknown, still waiting for us to chart it. Maybe in the end, the struggle isn't between the model and the data, but between our need for neat stories and the universe's delight and surprise. The cosmos is not a machine that obeys our calendars. It's an unfolding poem, written in starlight and gravity, where each new line changes the meaning of the last. And as Webb continues to read those lines aloud from the beginning of time, we find ourselves doing what science has always done best, listening, revising, and slowly learning the rhythm of creation all over again. When scientists speak of the timeline of the universe, they don't mean a line drawn across a page. They mean an unfolding, a rhythm of light, matter, and expansion that turns chaos into pattern. From the earliest fireball to the first stars, from galaxies to planets, every stage has its place in that rhythm. For decades, the melody seemed clear. Darkness, then dawn, then the slow brightening of the cosmic day. But when the James Webb Space Telescope opened its golden eyes, the rhythm shifted. The dawn came earlier than anyone had expected. For most of modern astronomy, the first billion years after the Big Bang have been a frontier hidden in fog. Earlier telescopes could glimpse only fragments of it, faint smudges at the edge of detection, like distant campfires glimpsed through mist. Hubble gave us the first hints, showing galaxies at redshift around 11, meaning their light had travelled for more than 13 billion years. But Webb sees deeper still, reaching redshifts of 13, 14, even beyond. Each step higher in that number takes us further back, closer to the first flickers of starlight, when the universe was only a few 100 million years old. In the standard picture, the timeline goes something like this. The Big Bang sets everything in motion. Within minutes, the lightest elements, hydrogen and helium, are born. Then, for nearly 400 million years, the cosmos is dark and featureless, filled only with drifting gas. Gravity slowly gathers that gas into denser clumps. At last, the first stars ignite, flooding the universe with ultraviolet light. That radiation tears apart the fog of neutral hydrogen, allowing light to travel freely. Astronomers call this great transformation reionization. The moment the universe became transparent, when darkness gave way to light. The galaxies Webb has discovered seem to push that transformation much earlier than expected. Their brightness and number suggest that the first generation of stars was already thriving, while the rest of the universe should still have been wrapped in its fog. If those galaxies truly existed so early, they might have been the ones that reionized the cosmos, ending the long night far ahead of schedule. To appreciate what that means, imagine standing in a dense mist at dawn. You can't see the sun yet, but you can sense it. A pale glow building somewhere beyond the fog. Then, all at once, the mist begins to thin, light spills through, and the landscape comes alive. That's what reionization was, the clearing of the cosmic fog. And what Webb may be telling us is that this sunrise began much sooner and spread much faster than our previous models allowed. This revelation has forced astronomers to revisit their calendars. Maybe the first stars formed not 400 million years after the Big Bang, but 250 million. Maybe galaxies began gathering material before the universe was even fully cooled. Some calculations now suggest that by the time the cosmos was 500 million years old, it was already full of starlight, a universe that, in cosmic terms, raced from infancy to adolescence in the blink of an eye. How could it have happened so quickly? One possibility is that the building blocks of galaxies, the small dense halos of dark matter, formed unusually early, giving stars a head start. Another is that those first stars were simply enormous and efficient, shining fiercely and dying young, flooding space with radiation that cleared the fog in record time. There's even the chance that black holes played a role, their energetic surroundings acting like cosmic flashlights, helping to ionize the gas around them. Yet, even as the timeline shifts, the harmony of the Big Bang itself remains intact. The beginning is still the beginning. What changes is how rapidly the universe evolved afterward, how quickly it learned to organize itself, to produce complexity. If anything, Webb's discoveries make that first billion years more interesting, more alive, not less. Of course, adjusting the cosmic calendar is no simple task. Scientists must tread carefully between data and interpretation. Redshift estimates can sometimes trick us. A dusty, nearer galaxy can masquerade as a pristine, distant one. Spectroscopic confirmation, breaking light into its precise wavelength, is the ultimate test. With each new observation, astronomers refine their timeline, cross-checking, recalibrating, comparing theories against the faint traces of light that arrive from the past. But the more they look, the clearer it becomes. The early universe was no quiet dawn. It was an explosion of creativity. Galaxies were forming faster, merging more often, and producing more stars than anyone had predicted. The cosmic web, the great lattice of filaments and voids that connect everything, was already beginning to stretch across space like a spider's silk. By the time our Milky Way's ancestors began to take shape, the universe was already full of structure, glowing islands in a vast sea of expanding night. There's a kind of poetry in that acceleration. We often think of time as a steady flow, but in those early eons it must have felt turbulent, if time could feel at all. Gravity was sculpting, radiation was sculpting back, and in that tension between pull and push, galaxies were born. The timeline, once thought to be smooth and predictable, now feels more like a symphony, crescendos, pauses and bursts of unexpected rhythm. And perhaps this is how it's meant to be. Nature doesn't follow our neat expectations, it dances to its own beat. The early cosmos may have been impatient, eager to fill itself with light, eager to begin telling stories long before we arrive to read them. For those who study cosmic history, this shift is more than an academic correction. It changes how we see ourselves. Every atom in our bodies was forged from those early generations of stars. If the timeline is faster, then the journey from chaos to consciousness was swifter too. The dust that became Earth, the molecules that became life, the thoughts now considering these questions, all arose from a universe that wasted no time in becoming capable of wonder. So when astronomers speak of a timeline in question, they aren't mourning a lost certainty. They're celebrating a mystery deepened. The universe has simply turned out to be more energetic, more creative, and perhaps more spontaneous than we ever dreamed. And as Webb continues to send back its golden images, each one a time capsule from an age when galaxies were just learning to shine, we may yet find that the cosmic dawn wasn't a single moment at all, but a long, luminous unfolding, a sunrise stretched across hundreds of millions of years, washing over everything, softly, patiently, until the universe was finally awake. In the early days after the James Webb Space Telescope began sending back its first images, headlines around the world seemed to sing the same refrain, that the telescope had broken the Big Bang, that galaxies older than time itself had appeared in its golden mirrors. The excitement was intoxicating and perhaps inevitable. After all, when you look into the universe's deepest past, every discovery feels like something miraculous. But as the first waves of astonishment settled, scientists began to do what they always do when the universe surprises them. They looked closer, measured again, and began to ask the quiet question that protects science from itself. Could it be a trick of light? Light is a patient messenger, but not a perfect one. By the time it reaches us, it has crossed billions of years of expanding space. It has been bent, reddened, dimmed, scattered, and sometimes disguised. The early galaxies that Webb sees are incredibly faint. So faint that the light from them could be counted in handfuls of photons, each one travelling for more than 13 billion years. A single misstep in how we interpret that faint glow could make something ordinary appear extraordinary. One of the simplest deceptions comes from dust. Tiny grains drifting between stars made of carbon, silicon and oxygen. Dust absorbs blue light more strongly than red, giving distant galaxies a warmer colour. To astronomers, colour isn't decoration, it's data. The redder a galaxy appears, the farther away it usually is, because the expansion of the universe stretches its light toward the red end of the spectrum. But if dust also makes a galaxy red, the two effects can blend like layers of paint. A nearby dusty galaxy might mimic the colour of one at extreme distance. Webb's instruments can distinguish between the two, but the line is delicate, like reading a faded manuscript under candlelight. Then there's the trick of gravity itself. Massive objects, stars, galaxies, and invisible halos of dark matter can bend space, curving the path of light as it passes. This is gravitational lensing, and it's one of nature's oldest illusions. When a heavy mass lies between us and something far away, it acts like a magnifying glass, making the distant object appear brighter and sometimes duplicated. On Webb's images, lensed galaxies often appear as graceful arcs, stretched by the curvature of space-time. But if the distortion is subtle, a faraway galaxy might seem far more luminous than it really is. Some of the impossible galaxies, it turned out, might have been magnified by cosmic lenses along the way. Astronomers treat every bright dot in Webb's data with suspicion and care, checking nearby regions of space to see whether there's a lensing cluster that could be boosting its light. It's a bit like studying a mirage. A shimmer on the horizon looks like an oasis, but it's really light bending in the heat. Still, the mirage is real in its own way. The light is bending, the shimmer is true. It's just that the story it tells needs to be read correctly. Even when there's no lens, light can still mislead. Measuring cosmic distance isn't done with a ruler. It's done by decoding the stretching of light, a quantity called redshift. For bright objects, scientists use spectroscopy. They split the light into a rainbow and look for specific dark lines, the fingerprints of elements like hydrogen and oxygen. Those lines shift toward red as the universe expands, and the degree of that shift reveals how far away the object is. But spectroscopy requires strong, clean light. For the faintest galaxies, astronomers often rely on a simpler method, photometric redshift, which estimates distance based on colour alone. Photometric methods can be deceived. Strong emission lines, bursts of light from hot gas, can make galaxies appear redder than they truly are, mimicking extreme distance. Webb's early data included several of these candidates, and when spectroscopy later confirmed their distances, some turned out to be nearer than first thought. But others, astonishingly, were exactly as far away as they seemed. The trick of light hadn't fooled everyone. Some of the impossible galaxies remained impossible. It's easy to forget that every number in a cosmology paper, every redshift, every luminosity, is built on years of careful calibration. Instruments like Webb's near-infrared camera and spectrograph must be tuned with almost absurd precision. Even a small error in how they measure wavelength can shift the inferred distance by hundreds of millions of light years. That's why teams across the world cross-check one another's results, comparing different instruments, independent data sets, and sometimes even rerunning entire analyses to ensure that what they're seeing isn't just an artifact. But there's beauty in that skepticism. The story of science is not only about revelation, it's also about restraint. Early excitement is part of the process, the heart leaping ahead of the data, the imagination racing toward possibility. But science's strength lies in its return to patience, its insistence on proof. The first whisper of discovery is like a note in the air, thrilling but incomplete until the orchestra joins in. So when Webb showed us galaxies that seemed too old, too bright, too massive, the question wasn't whether to believe or disbelieve. It was to listen more carefully to what the light was actually saying. Perhaps dust was colouring the picture. Perhaps gravity was amplifying it. Perhaps emission lines were confusing the story. Each possibility was a reminder that the cosmos has always been a master of disguise. And yet, even after all the corrections, after every test for illusion, the central mystery remains. Some of those galaxies are still there, distant, bright, massive, and unmistakably real. The tricks of light cannot explain them all. That's the quiet wonder of this moment in astronomy. We're not watching the fall of an old theory or the birth of a new one. We're watching science do what it does best. Pause, breathe, and learn how to see again. Every mirage tested brings the real oasis into clearer focus. Every illusion studied becomes another truth understood. In that sense, Webb's revelations haven't shaken the foundations of cosmology. They've strengthened them. They've reminded us that knowledge grows not just from discovery but from doubt. The same telescope that astonishes us with distant light also teaches humility, that seeing is never the same as knowing, and that even the clearest reflection may hide a deeper story waiting just beneath the glow. And perhaps that's why the universe remains so endlessly compelling. Even in the act of deceiving us, it's teaching us to look more deeply, to listen more softly, and to remember that every photon, no matter how ancient or faint, still carries both truth and mystery in equal measure. In the universe's early years, when everything was still new and restless, not all light came from stars. Some came from something deeper, darker even, engines hidden at the hearts of young galaxies, quietly devouring matter and shining with borrowed brilliance. These were the first black holes, ancient and insatiable, and some astronomers now suspect that they may be the secret behind at least part of the puzzle the James Webb Space Telescope uncovered: galaxies that appear older, brighter, and heavier than they should be. At first glance, the idea sounds strange. How could something that swallows light make a galaxy appear brighter? But black holes, when feeding, are not silent. As gas and dust fall inward, they form a spinning disk heated by friction to incredible temperatures. That disk glows across the electromagnetic spectrum, from high-energy X-rays to gentle infrared. In the centre of even a small galaxy, such a feeding black hole can outshine every star combined. Astronomers call these objects active galactic nuclei, or AGN for short. And when Webb began looking into the earliest epochs of cosmic time, the possibility arose that some of those dazzling, impossible galaxies weren't star factories after all. They were homes to newborn black holes burning bright with hunger. Imagine standing at the edge of a vast, dark forest. From afar, you see what looks like a cluster of lanterns hanging from unseen trees, glowing steadily through the night. You might think there's a village there, warm and thriving. But as you walk closer, you realise the lights are fires, fierce, concentrated, consuming what surrounds them. That's what an active black hole is like, not the calm glow of starlight, but the flare of something devouring its own fuel. When astronomers measure a galaxy's light, they interpret brightness as a clue to the number of stars it contains. More light usually means more mass, more maturity, more time for stars to form. But if even a fraction of that light comes from an AGN, the math changes. A small black hole, just a few million times the mass of our Sun, can mimic the output of billions of ordinary stars. It's a cosmic illusion, one that Webb's deep vision might be especially sensitive to, since it sees the faint infrared glow emitted by these hot disks. This doesn't mean the early galaxies are fake or misinterpreted. It means they might have been different in nature, not calm spiral systems filled with balanced starlight, but fierce, active environments where black holes grew side by side with stars, influencing each other in ways we are only beginning to imagine. In that sense, the early universe may have been as much a stage for black holes as for stars. Scientists are now using Webb's spectrographs to tease apart these signals, to separate starlight from black hole light. It's not simple. Both can produce similar colours in the infrared. But the fingerprints of an AGN are subtle and distinct. In the emission lines of hydrogen or oxygen, astronomers can detect the high temperatures and ionization patterns typical of accretion disks, the swirling rings of material that feed a black hole. In some of Webb's earliest data, those signatures appear faintly, suggesting that even at redshifts above 10, when the universe was less than 500 million years old, black holes were already lighting up the dark. If that's true, it raises another mystery. How did those black holes grow so quickly? To reach millions or even billions of solar masses in such a short span of time, they must have started large, perhaps formed directly from the collapse of massive gas clouds, skipping the usual step of being born from dying stars. These are sometimes called direct collapse black holes, and Webb may finally have the power to find them. They would represent a kind of fast track to cosmic maturity, galaxies that look old not because their stars aged, but because their cores did. In a way, this theory is comforting. It offers an explanation that fits within the existing rules of physics. No need to rewrite the beginning of the universe, just to widen the cast of characters that shaped it. It also reminds us how easily brilliance can deceive us. The light of an active nucleus is so intense that it drowns out everything around it, like a spotlight on a stage that hides the set and the actors. To see what truly lies behind that glare, astronomers have to peel away layer after layer of data until only the starlight remains. That process, the peeling back of illusion, is one of science's quiet arts. It doesn't happen in grand gestures but in small corrections, weeks of analysis, and the slow building of trust in a result. When the first Webb observations hinted at galaxies that seemed too grown up, it wasn't denial that made scientists cautious. It was respect for how easily the cosmos can disguise its truth. They knew that light, for all its honesty, can still tell half-truths, and yet even after accounting for possible AGN contamination, many of the early galaxies remain bright beyond expectation. Some may indeed harbour hidden black holes, but others appear powered purely by stars, exuberant, youthful, and unfiltered. The universe, it seems, has both kinds of brilliance, the borrowed light of hidden engines and the genuine glow of stars born in storms. There's a quiet metaphor there too, one that stretches far beyond astronomy. Not every brightness means maturity. Not every glow signals age. Sometimes what seems fully formed is still in the midst of becoming, and sometimes what burns hottest is also what fades fastest. The early cosmos in all its beauty was full of these illusions, but every illusion, once understood, brings us closer to the truth. As Webb continues to collect its faint gold-tinted data, each photon adds another brushstroke to the portrait of those first galaxies. Some will turn out to be bright with borrowed light, others with their own. Either way, both tell the same larger story. That creation was messy and magnificent, full of hidden engines and radiant disguises, and perhaps that's what makes the universe so endlessly fascinating. It doesn't hide its secrets to deceive us. It hides them the way a flame hides its core, to remind us that understanding requires not only seeing, but also patience, and the humility to admit that sometimes even light can lie. The early universe may have been small, but it was not quiet. It hummed with creation, with gas collapsing into stars so quickly that the cosmos must have glowed like a furnace. When the James Webb Space Telescope first saw those bright compact galaxies from just a few 100 million years after the Big Bang, one possible explanation rose to the top. Maybe these were not old galaxies at all, but young ones burning through their fuel in violent, short-lived bursts of star formation. To imagine it, picture a campfire. In the modern universe, most galaxies are slow fires, steady, patient, feeding on thin streams of gas that drift in from intergalactic space. Our Milky Way lights one new star every year or so, a quiet rhythm of birth and rest. But the first galaxies were nothing like that. They were cosmic bonfires, consuming gas at a furious pace, igniting new stars thousands of times faster. If our galaxy is a hearth, flame. The early ones were fireworks exploding against the night. In those early times, the raw material for stars, cold hydrogen and helium, was far denser than it is now. Space had not yet expanded into the vast emptiness we know. Gravity had an easy job. Everything was close together. When a patch of gas began to collapse, it did so quickly, spinning faster, heating up until nuclear fusion began in the cores of newborn stars. And because there was so much material nearby, one birth often triggered another. Supernovae, the death throes of massive stars, sent shockwaves through surrounding clouds, compressing them, prompting even more stars to form. It was a chain reaction, a cosmic wildfire. Astronomers call this efficiency star formation rate, a measure of how quickly a galaxy can turn its gas into stars. In the nearby universe, that rate is modest, a few solar masses per year, but in the galaxies Webb has uncovered, it may have reached hundreds or even thousands. Imagine a single galaxy giving birth to the equivalent of an entire star cluster every few weeks. It's not that these galaxies were large, many were tiny compared to our Milky Way. It's that they were furious, brief, bright flashes of creation in a young universe still learning the art of restraint. Part of what made them so efficient may have been the nature of their stars. Astronomers believe that the earliest generations favoured the formation of giants, stars many times the mass of our Sun. In later epochs, stars are born in a more balanced way. A few large ones, many small ones. But early on, the balance may have tilted toward the massive end. Scientists call this the top-heavy initial mass function, but you could think of it as the cosmos playing its music in high notes first. Those giants burned hotter, lived shorter, and ended their lives in spectacular explosions that scattered heavy elements into the void. Each of those explosions did more than light up the darkness. It enriched the surrounding gas, cooling it more effectively, making the next wave of star formation even easier. It's a feedback loop that could explain why Webb sees so many bright, chemically evolved galaxies so early. The more the universe built, the faster it learned to build. Still, such furious creation comes at a cost. When stars form too quickly, they consume their fuel almost as fast as they gather it. Within a few 100 million years, many of these early galaxies may have already exhausted their gas, fading into quiet remnants. Others merged, colliding to form larger systems, the ancestors of modern galaxies. What we see through Webb's mirror might be those short-lived moments of glory, the universe's first creative outburst before settling into the slower rhythms we know today. There's a kind of poignant beauty in that thought. These early galaxies shone so brightly that their light still reaches us across 13 billion years, yet their lives may have lasted only a heartbeat in cosmic time. They burned fast and vanished, leaving behind only their dust, their metals, and the faint afterglow that now whispers through our telescopes. For scientists, this picture, of extreme starbursts rather than impossible age, helps explain much of Webb's data without breaking the laws of physics. It suggests that the universe wasn't ahead of schedule, it was just running its opening act at full volume. When astronomers simulate such bursts on supercomputers, they find that if the early galaxies formed stars 10 times more efficiently than expected, their observed brightness matches Webb's findings almost perfectly. In this view, there's no need for new physics, only new appreciation for how lively the young cosmos was. The laws of nature stayed the same, the conditions simply amplified them. In a dense, pristine universe filled with gas eager to collapse, gravity worked with fierce precision. The first stars weren't hesitant, they were impatient. Yet the idea of efficiency doesn't fully capture the wonder. What these galaxies represent is creativity under pressure. In the same way that life on Earth thrives in harsh environments, the cosmos itself seems to have flourished in its most intense moments. Where matter gathered most densely, it transformed itself into light and structure, almost as if it couldn't help it. If you could stand inside one of those early galaxies, impossible of course, but imagine it, the sky would never truly be dark. Massive stars would crowd the heavens, their blue-white light so strong that shadows would hardly exist. Nebulae would stretch across the sky like living veils, glowing with the radiation of newborn suns. The airless silence would be filled with motion, with energy, with the raw, soundless roar of creation itself. In a sense, Webb's discovery of these burst makers is a reminder that the universe's first art form was speed. It didn't tiptoe into existence, it leapt. The galaxies we see at the edge of time are proof of that wild beginning, bright sparks of cosmic ambition, making stars faster than logic should allow, faster than patience could imagine. And though their light has travelled for billions of years to reach us, it still carries that sense of urgency. When we look at them, we are seeing the universe's first breath, not calm, not measured, but joyous, chaotic, and alive. Perhaps that's why the light feels so warm, even after so many eons of travel. It's not only the glow of physics at work, it's the echo of creation's first heartbeat, a reminder that the cosmos, at its core, has always known how to burn bright when the moment calls for it. Beneath every galaxy, unseen but indispensable, lies something silent, a scaffold made not of stars or gas but of invisible matter. Astronomers call it dark matter, though the name is misleading. It isn't truly dark, it simply doesn't interact with light. It neither glows nor reflects, neither burns nor scatters, and yet without it, there would be no galaxies at all. It is the quiet architect of everything we can see, the invisible blueprint of structure in the cosmos. When the James Webb Space Telescope revealed massive luminous galaxies forming astonishingly early, one of the first questions cosmologists asked was whether dark matter could explain their speed. Perhaps, they thought, the scaffolding was built sooner and more efficiently than we imagined, allowing stars and gas to collect quickly inside. The standard cosmological picture, the lambda CDM model, already relies on dark matter as the main builder of structure. But what if those builders worked over time in the universe's youth? To picture how it happens, imagine the early cosmos as a vast mist of invisible material, sprinkled with tiny fluctuations, denser spots, barely one part in 100,000 thicker than their surroundings. Over millions of years, those faint differences grew. Gravity tugged matter toward the denser regions, forming clumps that drew in more and more material. These became the first halos of dark matter, gravitational wells into which normal matter, made of atoms, began to fall. Each halo was like an invisible cocoon. Inside, gas cooled, condensed, and eventually formed the first stars. Outside, the halos merged, combining into larger ones, pulling their luminous contents together. This process, repeated countless times, built the cosmic web, a lattice of filaments and nodes stretching across space, where galaxies reside like dewdrops on a spider's strand. In most simulations of cosmic evolution, this process takes time. Small halos appear first, then merge into larger ones. The first galaxies, according to earlier predictions, should have formed when the universe was about 400 million years old. But Webb's data shows galaxies already thriving 200 million years earlier. To reconcile that, scientists are exploring whether dark matter halos might have collapsed faster than expected, forming early neighborhoods before the cosmic city was officially planned. It's a humbling reminder that gravity, when it finds enough raw material, wastes no time. Even a slightly higher density of matter in the early universe could have sped up collapse dramatically. If those halos formed earlier, they would have provided the perfect stage for rapid star formation, explaining why Webb sees bright structured galaxies where theory expected only chaos. Dark matter doesn't just form scaffolds, it shapes destiny. The strength of its gravitational pull decides whether a galaxy can hold onto its gas or lose it to stellar winds. In regions where dark matter halos were massive, gas remained bound, feeding wave after wave of starbirth. In smaller halos, radiation from the first stars might have blown the gas away entirely, leaving ghostly empty shells. The galaxies we see from Webb's deep fields could be the fortunate ones. Early overachievers formed within the most powerful halos. Some researchers are now running new computer simulations, adjusting the initial conditions to match Webb's surprising results. These simulations are miniature universes in themselves, coded into the circuits of supercomputers, digital realities where billions of particles dance under gravity's pull. When they tweak the parameters slightly, just a bit more density here, a little faster cooling there, the simulated galaxies begin to appear earlier, brighter, and more organized, just as Webb observes. But the mystery remains. Why would the real universe favor such early construction? It might be simple chance that Webb's gaze happened to fall on an unusually dense region, a corner of the cosmos where dark matter's architecture developed ahead of schedule. Or it might hint that our understanding of dark matter's behaviour, subtle as it is, still needs refinement. There's an elegance in that thought. For decades, dark matter has been the most faithful of cosmic companions, quietly agreeing with almost every observation. It explains the rotation of galaxies, the clustering of matter, and the shape of the cosmic microwave background. But Webb's data is a soft tap on the shoulder, a reminder that even old companions can surprise us. Maybe dark matter interacts slightly with itself, clumping faster than expected. Or perhaps its distribution in the early universe was just a touch more uneven than our instruments could detect. Whatever the cause, the story remains beautiful. Galaxies rising from invisible foundations, sculpted by something we can't see but can feel through gravity's patient hand. The light Webb records is only the surface of the sculpture. Beneath it lies the structure carved from darkness. If we could see those early halos directly, not their luminous contents, but the dark shapes themselves, the universe would look like a lacework of shadows. Filaments would stretch between clusters, and at their intersections bright knots of starlight would bloom. In those knots, gas would spiral inward, feeding both stars and perhaps the first black holes. The architecture of everything we know, stars, planets, even us, began in those hidden intersections. There's something deeply moving about that idea, that the foundations of beauty can be invisible. The glow of a galaxy is what catches our eyes, but it is gravity's silent choreography that makes that glow possible. The halos collapse quietly, without colour, without sound, and from their stillness, the universe learns how to shine. Even as we speak of them in metaphors, cocoons, webs, scaffolds, we know we're reaching for images to describe something that may forever elude sight. Yet, we can trace its fingerprints in every observation Webb makes. The spacing of galaxies, their clustering, their very existence, all whisper the same secret. You're seeing only the surface. Perhaps in a way, dark matter is the universe's way of reminding us that not all truths must be visible to be real. The most essential forces, gravity, time, love, curiosity, all share that same invisible touch. They shape what we see, even if we never see them directly. So as we watch Webb uncover more early galaxies, dazzling in their youth, we might imagine the hidden architects beneath them, vast halos collapsing faster than our equations once allowed, quietly building the framework for light to exist. They worked unseen, and yet everything luminous today is their handiwork. And maybe that's the most poetic truth of all, that even in the universe's first rush to create, there were hands we couldn't see guiding the process, patient, invisible, and absolutely necessary. Every galaxy, every planet, every living thing owes its existence to a generation of stars that no longer shines. They were the first, immense, unbalanced, and brilliant beyond comprehension. Astronomers call them Population 3 stars, the original architects of everything that came after. They were made of only the simplest ingredients, hydrogen and helium, the lightest elements born in the Big Bang. No carbon, no oxygen, no iron, nothing that could cool gas efficiently or build planets. Yet from that simplicity came the first spark of complexity. The James Webb Space Telescope may be catching their echoes. In several of the most distant galaxies it has observed, there are signs of intense ultraviolet radiation and chemical purity, clues that some of those stars might still be visible, or that their ashes remain embedded in the light we see. If that's true, Webb is not just looking at early galaxies, it's peering into the universe's first experiment with starlight itself. To understand what made these stars special, imagine a cosmic landscape where everything is new and smooth. The first halos of dark matter have collapsed, pulling in hydrogen gas from the surrounding void. The gas cools slowly, because without heavier elements it can't radiate heat efficiently. As a result, the gas clouds grow massive before finally collapsing under their own gravity. When they ignite, the stars they form are enormous, perhaps 100 or even several hundred times the mass of our Sun. Their lives are brief, lasting only a few million years. But in that short span, they reshape the universe. Their light is fierce, flooding space with high-energy photons that begin to tear apart the fog of hydrogen left over from the Big Bang. Their interiors are forges, fusing hydrogen into helium, helium into carbon, oxygen, and heavier elements. And when they die violently, as supernovae that scatter those new elements into the surrounding gas. Each explosion is both an ending and a beginning. Before these first stars, the universe was chemically simple. After them, it became rich. The oxygen you breathe, the calcium in your bones, the gold on your finger, all trace their ancestry back to those first enrichment events. In a poetic sense, we are the afterglow of those deaths, the cooled remnants of ancient fire. Astronomers call this process metal enrichment, though in their language, metals mean all elements heavier than helium. When Webb detects signs of carbon, oxygen, or silicon in galaxies that existed when the universe was only a few 100 million years old, it's detecting the fingerprints of Population 3's legacy. It means that several generations of stars have already lived and died, seeding space with the materials of future worlds. Some of the evidence comes from Webb's infrared spectra, the detailed rainbows of light that reveal which elements are present in a galaxy. In one young system, scientists found an unusual ratio of oxygen to iron, a hallmark of massive stellar explosions. In another, they saw a sharp absence of dust where dust should already have formed, hinting that they were witnessing the transition, the moment when the first pure stars were giving way to the next, slightly more complex generation. It's like catching the world halfway between innocence and experience. To put this in perspective, consider how fast the transformation occurred. The universe began with only hydrogen and helium. Within just a few 100 million years, it contained all the essential elements for planets and life. If cosmic history were a single calendar year, that chemical leap from simplicity to richness would have happened before the first day of February. The rest of the year, everything else, would be the unfolding of that gift. There's another mystery hidden within this story. Population 3 stars were so massive that some of them may have collapsed directly into black holes without exploding at all. Those black holes could have served as the seeds for the supermassive giants we find at the centres of galaxies today. If true, then even in death, the first stars were builders, sculptors of gravity wells that would later anchor galaxies and control their evolution. In that light, Webb's discoveries are not just observations of distant light. They're glimpses of inheritance. Every atom in your body has been through this cycle of birth and death countless times, fused in stars, scattered by explosions, reassembled in new forms. The iron in your blood may once have been part of a star that shone only for a few million years near the edge of the visible universe. The same universe now reflected in the telescope's golden mirrors. To many scientists, the search for Population 3 stars is almost spiritual, not in a mystical sense, but in its quiet reverence for origin. We have equations to describe fusion, models to predict luminosity, and computers to simulate collapse. But standing before Webb's deep field images, none of that fully captures the feeling. To realise that you are looking at the light from the first stars ever born, light that has travelled for more than 13 billion years, is to feel time collapse into a single, tender moment. If Webb eventually confirms the spectral signature of an untouched, truly metal-free star, one that has never been enriched by previous generations, it will be like finding the first heartbeat in cosmic history. For now, what we see are their footprints, galaxies glowing with the aftermath of their brief lives, space infused with the elements they left behind. There's a quiet lesson in that. The first generation of stars didn't last long. But they didn't need to. Their purpose wasn't endurance, it was transformation. They took a silent, colourless universe and turned it into one capable of complexity. In their deaths, they made everything else possible. The dust that would form planets, the carbon that would form life, the light that would someday find its way into a telescope orbiting a tiny blue world. So when you hear the term Population 3, don't think of a scientific label. Think of it as a name whispered for the ancestors of everything. The first storytellers in a language of light. The first to show the cosmos that even in its vast emptiness, it could create beauty, and in doing so, begin a chain of creation that has not stopped since. Their story isn't one of loss, but of legacy. And every time Webb detects the faint glow of heavy elements where none should yet exist, it's as though those first stars are still speaking, their voices carried on beams of ancient light, saying softly across eternity, "We were here, we burned, and you are the proof." There was a time, long before the first galaxies took their shapes, when the universe was wrapped in darkness. Not the darkness of nothing, but the soft, invisible kind that hides potential. After the Big Bang, space was filled with hydrogen gas, cool and quiet, stretching endlessly in every direction. For hundreds of millions of years, that fog absorbed nearly all light. If you could somehow stand there, you would have seen nothing at all. No stars, no galaxies, just an infinite sea of gentle shadow. And then, suddenly, something changed. Tiny points of light began to flicker into existence, like candles appearing one by one across a vast night. That awakening is what astronomers call the era of reionization, the moment the cosmos began to see itself. When the first stars ignited, their ultraviolet light struck the surrounding hydrogen atoms, stripping away their electrons and turning neutral gas into charged plasma. This process, reionization, gradually cleared the cosmic fog, allowing light to travel freely for the first time since the universe's birth. It was, in a sense, the second dawn, the opening of the sky. The James Webb Space Telescope is giving us our clearest view yet of that transition. Its deep infrared gaze can detect the faint galaxies responsible for this transformation. Small, compact, and countless. Earlier telescopes could only glimpse the end of the process when the universe was already mostly transparent. Webb, however, is showing us the beginning. The first candles in that immense night. In Webb's images, astronomers see something unexpected. Not a few bright sources, but many. The early universe seems crowded with tiny galaxies, each producing light intense enough to carve away at the fog. Individually, they are faint. Collectively, they are powerful. Together, they may have generated enough radiation to complete the reionization of the cosmos hundreds of millions of years earlier than previously thought. It's a humbling vision. The great clearing of darkness wasn't accomplished by a few cosmic giants, but by a chorus of small voices. Thousands upon thousands of miniature galaxies, each burning with determination, lit the path to the transparent universe we know today. Like a field of fireflies turning dusk into glow, they transformed the cosmos one photon at a time. Scientists once wondered whether the first stars alone could have done it. But Webb's discoveries suggest that these galaxies, and perhaps the first black holes too, work together in a cosmic collaboration. Some galaxies hosted clusters of massive stars, their radiation intense enough to ionize vast regions of space. Others may have contained early black holes whose hot, accreting disks shone with enough energy to pierce through the hydrogen fog. Bit by bit, bubble by bubble, the universe became clear. It's difficult to convey the scale of that change. At the start of reionization, light could travel only a few light years before being absorbed. By the end, it could cross billions. The universe went from opaque to transparent, from confinement to openness. In human terms, it was like taking your first breath after a long sleep. The moment the cosmos itself became visible. One of Webb's most remarkable findings is that many of these early galaxies are far more numerous than predicted. Even the smallest ones, no more than a few million solar masses of stars, appear to have contributed to the ionization flood. Some formed in isolation, others gathered in clusters, their combined light creating expanding bubbles of ionized gas that overlapped and merged. Eventually, those bubbles joined into one great clearing, leaving the universe we see today, a vast, luminous web stretching across space. The story of reionization is also the story of transformation through cooperation. No single star could have changed the universe alone, but together millions did. It's an echo of a truth that repeats everywhere in nature. Complexity arises from connection, from many small efforts woven into one grand design. Webb's role in this story is equally poetic. Its mirrors, cooled to nearly absolute zero, are themselves part of the long chain of light that began in those first galaxies. The photons it detects were released more than 13 billion years ago, long before Earth existed. They have been stretched by expansion, softened into infrared, and now rest gently on detectors built by a civilization that can finally listen to them. It's as if the universe, after so long, is whispering back to itself. I remember when I first learned to shine. For astronomers, understanding reionization isn't just about solving a puzzle. It's about tracing the moment when the cosmos became visible, when it stopped hiding its beauty. Before that, the universe was a dark ocean. Afterward, it was a tapestry of light and structure, filled with galaxies, stars, and the seeds of everything to come. The process likely ended when the universe was around 1 billion years old. By then, the fog was gone, and starlight could travel freely. But that clear sky came at a cost. The same radiation that illuminated the cosmos also burned away the cold gas that future generations of stars needed. Star formation slowed. The universe began to move from a frantic adolescence into a calmer maturity. Light had conquered darkness, but in doing so, it had changed the balance forever. Even now, billions of years later, we can still see the faint signature of that transformation, imprinted in the cosmic background. A subtle difference in temperature and polarization that tells us when the fog lifted. And thanks to Webb, we can finally see the actors that made it happen. Those tiny, defiant galaxies shining with impossible courage. If you could watch the reionization of the universe in real time, it would not be a sudden explosion of brightness. It would be more like dawn on a foggy morning. Slowly the haze would thin. Patches of clarity would appear, revealing glimpses of structure. Then gradually the light would spread until the whole sky glowed. That gentle unveiling is what Webb is showing us. Not chaos, not violence, but emergence. And perhaps that's why this story feels so human. Every life, in its own way, repeats that pattern. We begin in darkness, uncertain, unformed. Then, through connection and transformation, we find our light. The universe's first dawn is still echoing inside us, not just as atoms forged in early stars, but as the same drive toward illumination, the same instinct to see and be seen. The great reionization wasn't only the moment when the cosmos became transparent, it was the moment when it learned to share its light, to scatter it across time, so that, billions of years later, we might look back and understand that from darkness, beauty always finds a way to emerge. Whenever the universe surprises us, there's a familiar whisper that rises among both scientists and dreamers. Maybe everything we know is wrong. It's not cynicism, it's curiosity running wild. The same curiosity that drives children to pull apart clocks to see what makes them tick. When the James Webb Space Telescope began revealing galaxies that seemed impossibly bright and well-formed just a few 100 million years after the Big Bang, that whisper returned louder than ever. Headlines called it the end of cosmology, a revolution, even proof that the Big Bang never happened. But science, for all its boldness, is built on patience. The temptation to rewrite everything is as old as discovery itself. Yet, each time we've done so, it has only been because nature demanded it, not because we grew restless with the story we already had. It's easy to understand the appeal. The Big Bang Theory is one of the great human triumphs, a simple, elegant narrative describing how everything began. It has survived countless tests, from the faint cosmic microwave background that still hums around us, to the abundance of light elements in stars and galaxies, to the slow stretching of space that continues even now, but it also carries a kind of gravity on its own. After decades of near-perfect agreement between theory and observation, even a small anomaly can feel like a crack in a dam. Webb's early galaxies were just that, dazzling little cracks that seemed to let in a flood of wonder. For a moment, some imagined that the whole picture might collapse, that perhaps the universe didn't begin with a singular event, or that time itself loops like a tide, rising and falling forever. Others suggested subtler shifts. What if the early universe expanded at a different pace than we thought? What if the speed of light varied slightly in those first instants? Or what if our understanding of dark matter, that invisible scaffold of creation, is incomplete? Each of these ideas, however speculative, carries the same spark, the yearning to find new language for an ancient mystery. But before the ink dries on any new cosmic story, science insists on humility. The Big Bang remains not an act of faith, but an ever-tested explanation, still the most consistent framework we have. Its predictions fit with the cosmic microwave background, with the observed ratios of hydrogen to helium, with the distribution of galaxies across space. Webb's discoveries, astonishing as they are, don't erase that framework. They simply ask us to colour it with finer detail, to adjust the tempo rather than rewrite the symphony. Still, we can admit how intoxicating the thought of new beginnings can be. Imagine learning that time itself might have existed before the Big Bang, that our universe could be just one cycle in an eternal rhythm of expansion and collapse. Some physicists explore this idea through cyclic or bouncing models, where a previous universe compressed and rebounded into ours, leaving faint imprints in the cosmic background. Others consider whether what we call the Big Bang was less an explosion and more a transition, a change of state in a larger hidden reality, the way water becomes vapour when it boils. There are even wilder musings, that the speed of light or the strength of gravity might have evolved slightly over time, that the early universe could have been shaped by exotic fields or dimensions beyond the ones we know. Each idea stretches imagination to its edge, and while none have yet replaced the Big Bang, they remind us how alive the scientific imagination truly is. Yet for all these daring possibilities, most cosmologists remain anchored to evidence. They see in Webb's findings not the death of the Big Bang, but its refinement, the discovery that creation may have unfolded faster and more dynamically than our equations once allowed. In that sense, Webb isn't destroying the timeline, it's sharpening the focus, showing that the universe wasted no time in finding form. And there's something quietly reassuring in that. The Big Bang was never meant to explain everything, only to mark a beginning. The first frame in a film whose later scenes we are still uncovering. If those early galaxies are brighter or older than expected, it doesn't mean the first frame is missing. It means the film is richer than we imagined. The human mind is drawn to revolutions because they feel like progress. We love the drama of tearing down old walls, but the real work of science often lies in renovation, not demolition, in expanding rooms, widening doorways, letting in more light. That's what Webb has done. It's built an extension to our cosmic house, a new wing opening onto a view we didn't know was there. The foundation remains the same. Still, there's no denying the poetry of questioning. Somewhere inside every scientist is the same ancient curiosity that looked up at the stars and asked why. And each time a discovery pushes against the edges of knowledge, that question stirs again. Could there be something beyond our beginning? Some deeper cause? Some older universe whispering from before time began? The answers may stay out of reach, but the asking itself keeps us alive to wonder. Perhaps that's what the Big Bang truly represents. Not a single explosion in space, but the ongoing expansion of understanding. Every new telescope, every observation, is part of that same unfolding. The universe doesn't fear revision, it invites it. It grows with us as we learn to listen more carefully to its light. So the temptation to rewrite everything is not wrong. It's a sign of health, a pulse that reminds us that knowledge is alive. What matters is that, in our rush toward new stories, we remember to honour the old ones too. They are the scaffolds that let us climb high enough to see the horizon. The Big Bang endures because it works, because it explains, because it hums in harmony with everything we can measure. But beyond that harmony, there will always be faint notes of dissonance, small, beautiful mismatches like those early galaxies Webb found. They're not threats to the song. They're invitations to listen closer. Maybe, in time, one of those notes will indeed lead us to a new melody, a new understanding of origins that no one can yet imagine. But until then, the music plays on, and we, patient listeners that we are, will keep tuning our instruments, one observation at a time, to the rhythm of the universe itself. Every few generations, science faces a moment when the familiar map of reality seems to blur at the edges. The discoveries made by the James Webb Space Telescope are one of those moments, not because they destroyed the map, but because they revealed more terrain beyond it. The Big Bang Theory, far from being undone, is finding itself renewed, challenged, and refined into sharper focus. It's as though Webb has turned up the brightness on a picture we thought we already understood, showing new details that were there all along, waiting to be seen. The Big Bang remains our best explanation for how everything began. It describes not an explosion in space, but the expansion of space itself, a stretching of distance, a blooming of possibility. Every galaxy, every atom, every breath of air carries the echo of that moment. The faint microwave radiation that fills the universe, the afterglow of creation, still hums around us, perfectly matching predictions made decades before it was even detected. The abundance of hydrogen, helium, and lithium in the cosmos aligns with the calculations of that first cosmic furnace. These are not just ideas, they are measurements, tested again and again, as dependable as sunrise. What Webb has done is not to contradict this foundation, but to deepen it. By seeing further back than ever before, it's revealing how quickly the young universe organised itself, how gravity, matter and time worked together to create galaxies earlier than our equations predicted. It's like finding an artist's sketch underneath a finished painting, the outlines of creation drawn faster and with more confidence than we expected. When the first murmurs of Big Bang is broken appeared, cosmologists smiled knowingly. They had heard similar whispers before, when we first discovered cosmic acceleration and named it dark energy, when we first measured the rotation of galaxies and found it didn't match visible matter, when the cosmic microwave background was first mapped in detail. Each time the model didn't collapse, it evolved. It absorbed the new data, adjusted, grew stronger. That's what living theories do. They adapt to truth. In the same way, Webb's discoveries are now being woven into a richer narrative. They show that the universe may have formed its first stars and galaxies faster than we thought, but still within the same cosmic timeline. The expansion rate, the age, the background radiation, all remain beautifully consistent. The Big Bang doesn't fall apart under scrutiny, it breathes. If the early galaxies appear older, it may be because the physics of star formation was more efficient back then, or because dark matter halos collapsed sooner, or because black holes and supernovae accelerated chemical enrichment. None of those explanations violate the Big Bang. They simply reveal how vibrant and creative the early universe was, how quickly chaos learned to compose itself into order. It helps to think of the Big Bang not as a single event long ago, but as a continuing process of unfolding. Space still expands, galaxies still drift apart. The echo of that first expansion is written in the redshift of light, in the very fabric of time. In a sense, the Big Bang never ended. It only changed tempo. What we call the present is just one movement in that ancient symphony. Webb's work, then, is like a rediscovery of the overture. It lets us hear the first notes more clearly, and in doing so, we appreciate the entire composition more deeply. Those galaxies at redshift around 13 are not older than the universe. They are simply the universe's earliest improvisations. Vast, brilliant, and full of confidence. The endurance of the Big Bang model doesn't come from stubbornness, but from its elegance. It connects phenomena across scales that seem impossibly distant from one another. The expansion of space explains the cooling of radiation. That cooling explains the formation of hydrogen. Hydrogen's abundance explains the birth of the first stars, and so on, all the way to the carbon in your breath and the calcium in your bones. It's a story so coherent that even its mysteries, dark matter, dark energy, inflation, feel like invitations rather than contradictions. Still, there's a quiet humility in how scientists talk about it today. They no longer speak of the Big Bang as the absolute beginning of everything, but as the earliest moment we can meaningfully describe. What came before, if before even has meaning, remains unknown. Perhaps there was a prior universe that collapsed and bounced into ours. Perhaps quantum fluctuations seeded reality itself from a timeless state. We don't yet know, and that uncertainty isn't a flaw, it's part of the beauty. The Big Bang is not the end of the story of beginnings, it's the first page we can read clearly. When you hear scientists defend the Big Bang, they're not defending dogma, they're defending evidence, the weight of decades of measurements that all point to the same melody of expansion. They're also defending something subtler, the idea that truth, even cosmic truth, can be both stable and evolving at once. A model can remain solid while still expanding at its edges, much like the universe itself. In that way, science mirrors the cosmos it studies. Theories grow, stretch, and adjust just as galaxies drift and change. Each new observation becomes another star in the constellation of understanding, brightening the picture without erasing the old ones. Webb's revelations aren't an end, they're a renewal, a reminder that even the most established truths still have room to breathe. So the Big Bang still stands, not as a monument carved in stone, but as a living framework, open to revision, expansion, and wonder. It's not a relic of certainty, it's a vessel of curiosity. The more we learn, the more it accommodates. If you close your eyes and imagine the moment of creation, don't picture an explosion in space. Picture the stretching of space itself, every point moving away from every other, like the surface of a balloon being inflated. Inside that stretch, time flows, matter condenses, and stars form. That motion continues even now. The Big Bang is not past tense. It's the quiet expansion that carries you, the Earth, and every galaxy outward still. And perhaps, as we stand at this point in history, our telescopes orbiting above the planet, our questions reaching further than ever, we can feel the same pulse that began it all. The pulse of a universe that refuses to stand still, that insists on becoming more complex, more luminous, more alive. The Big Bang is not just an origin, it's an ongoing act of creation, and we are still inside it. Each thought, each discovery, another ripple in the first and longest breath of time. Every so often, the universe acts like an artist who glances at their own painting and smiles, realizing it has taken on a life beyond their control. The James Webb Space Telescope's discoveries feel like that, as if the cosmos itself had paused for a moment of self-awareness, surprising even the mind that studies it. We are used to imagining the universe as predictable, ruled by equations and constants. But what Webb reminds us is that nature has imagination too. Science often moves in straight lines, from question to answer, from prediction to proof. But progress rarely feels linear when it's happening. It feels more like a long conversation, full of interruptions, unexpected laughter, and quiet realizations. The Webb telescope's early findings, galaxies that seem too luminous, stars that seem too mature, black holes that appear too soon, are not contradictions. They are the universe leaning closer, whispering, "Look again." To scientists, that whisper is exhilarating. It means there's something new to learn, some hidden logic waiting to be uncovered. For decades, astronomers have followed the script written by the Big Bang and refined by observation. They knew roughly when the first stars should form, how galaxies should grow, when reionization should clear the cosmic fog. But Webb has added a new chapter, one that's faster, more dynamic, more intricate than expected. Instead of dissonance, it's harmony with added complexity. The melody of creation playing in higher tempo. There's something beautifully human in how scientists respond to this kind of surprise. First comes wonder, the breath held before comprehension. Then comes caution, the slow return to data, the long nights of checking calibration files and testing hypotheses. And finally comes acceptance, not of defeat, but of enrichment. What was once a simple story becomes a more nuanced one, filled with new colours and deeper shadows. The Big Bang remains the stage, but the play has grown more elaborate. If you look back through the history of science, every great leap began this way. When astronomers noticed that Mercury's orbit didn't follow Newton's laws perfectly, it wasn't the end of Newtonian physics. It was the beginning of Einstein's relativity. When physicists found that energy and matter behaved strangely at atomic scales, it wasn't a failure of classical mechanics. It was the dawn of quantum theory. Each surprise wasn't a rejection of truth, it was truth growing larger. Webb's discoveries belong to that same tradition. The early, overachieving galaxies are like Mercury's orbit, small deviations that could signal a deeper harmony yet to be written. Whether they point to new physics or simply reveal more efficient star formation, they remind us that the universe is still teaching, still evolving, still speaking a language we haven't fully learned. There's humility in that realization. We tend to think of science as conquering ignorance, as reaching a summit where answers stand waiting. But in truth, every discovery only expands the horizon. Each time we climb higher, the view widens and we see how much more there is to explore. Webb's view of the early universe doesn't close a chapter, it opens several more, each asking a quieter, subtler question than the one before. And there's comfort in this unendingness. The fact that the universe can still astonish us means it hasn't run out of wonder. It means that after billions of years, it's still unfolding in ways that challenge even our most elegant equations. Maybe surprise is the universe's way of staying alive, a gentle refusal to let us believe we've reached the end of the story. Philosophers sometimes speak of the limits of knowledge, but perhaps it's better to call them the edges of illumination. What Webb does is push those edges outward. It gathers light that has been travelling since the dawn of time and offers it to us, saying, "Here, this too is part of you." Because it is. The light Webb captures isn't foreign. It's ancestral. It's the glow of the first stars whose ashes became our elements, whose radiation shaped the very space in which we exist. When we study them, we're studying the memory itself, the universe remembering how it began. Even the idea that the cosmos can surprise itself isn't as strange as it sounds. The universe is not a fixed creation, completed long ago. It is an ongoing performance, improvising through feedback and interaction. Stars form and die, seeding galaxies with the ingredients for future generations. Black holes consume and recycle, regulating the pace of growth. And consciousness, our ability to observe and reflect, is one of the newest instruments in this cosmic orchestra. Through us, the universe becomes aware of its own complexity. When Webb peers across 13 billion years, and we interpret that light, the universe is, in a way, looking back at itself. There's a quiet poetry in realizing that every measurement, every spectrum, Every pixel of deep field image is a dialogue between what was and what is. The galaxies Webb observes have long since changed or vanished, yet their light continues to tell their story. And in decoding that story, we become the universe's listeners, its historians, its dreamers. It's tempting to think of science as cold or mechanical, but at moments like this, it feels almost tender. It's an act of devotion, of paying attention so carefully that the universe's secrets feel comfortable enough to speak. When we find anomalies, when our models falter, we're not failing. We're being invited to listen more closely. The cosmos, it seems, has a sense of timing. Just when we begin to think we've understood it, it offers a small reminder. I still have surprises left. Perhaps that's the essence of discovery. Not conquest, but conversation. The Webb telescope doesn't just collect light. It listens for tone, for the soft resonance of meaning beneath the data. Every unexpected brightness, every strange spectrum is a note in that continuing dialogue. And so, as the telescope drifts silently at its distant orbit, sending back images of galaxies that existed when time itself was young, we can take comfort in knowing that our story is part of theirs. The universe surprises itself through us. We are both the observers and the observed, both question and answer, both the student and the mirror in which the cosmos sees its own face reflected in the glow of understanding. That's the quiet magic of moments like these. They remind us that knowledge isn't a wall we build, but a horizon we chase, one that always stays just far enough ahead to keep us moving, curious and awake. The universe will continue to astonish us, not because our models are wrong, but because it is infinite in its creativity. And maybe, in that endless cycle of question and revelation, lies the deepest kind of beauty. A beauty that doesn't fade with certainty, but grows with wonder. There's a moment just before sunrise when the world holds its breath. The air is still, the horizon faintly silver, and everything feels expectant, as if creation itself is about to start again. The James Webb Space Telescope gives us something like that feeling on a cosmic scale. Each time we look deeper into space, we are standing at the edge of the universe's first morning, watching the light of the earlier stars break through a darkness that once seemed endless. And yet, in that silence, there's a kind of peace. Not the thrill of revelation, but the calm recognition that we're part of that same awakening. By now, we've followed Webb's journey from discovery to humility, from impossible galaxies and hidden engines to quiet acceptance that the universe is both faster and wiser than we thought. We've seen how dust disguised youth as age, how black holes shone like counterfeit suns, how invisible scaffolds of dark matter cradled the first stars. And after all the questions, the recalibrations, and the quiet awe, what remains isn't confusion, it's serenity. Because the truth Webb reveals is not chaos, it's continuity. The Big Bang still hums softly beneath everything, the same pulse that began time still beating through every particle, every photon, every thought. The universe hasn't rewritten its story, it has simply added more verses to the song. And what a song it is, one that began as a whisper of hydrogen, grew into the roar of stars, and now finds its echo in the quiet minds of the beings who finally learned how to listen. When we talk about the light from those earliest galaxies, we often forget how long it has travelled. 13 billion years. That's more than half the age of everything. In that time, stars have burned and died, galaxies have collided, planets have formed, and life has risen and wondered. Yet the light from those first dawns has crossed all that distance, all that history, to reach a mirror of gold floating beyond our moon. And when that light touches Webb's instruments, it's not just data. It's an embrace, a handshake across time. It's hard to think of another instrument that captures the paradox of existence so perfectly. Webb is an object of metal and precision, governed by math and logic. But the thing it measures, the soft birth of light, belongs to poetry. It looks outward, yet everything it finds also turns inward, reflecting on us. When you see a deep field image, that swarm of galaxies scattered like dust on velvet, you're not just looking at the past. You're looking at the ingredients of yourself, the oxygen in your lungs, the calcium in your teeth, the iron in your blood. All of it was forged in the stars whose first light Webb now captures. There's something deeply comforting about that. For all our modern noise, we're still connected to that ancient silence. Every photon Webb catches has travelled not just through space, but through patience. It waited, untouched, until we were ready to see it. Until a species that once mapped stars with sticks and stones built a telescope delicate enough to listen to the universe breathe. And perhaps that's the greatest story of all. Not that we found answers, but that we found a way to ask questions with such grace. The telescope doesn't conquer the unknown, it courts it. It doesn't demand truth, it waits for it. The way it observes is almost human in its gentleness, steady, curious, unhurried. Through it, we've learned that the universe rewards those who look softly. When Webb sends back its light, it's easy to imagine it speaking, not in words, but in the language of colour and time. I was here, it seems to say. I burned. I changed. I passed on what I could, and in hearing that we hear something of ourselves. We too burn, with curiosity, with love, with longing to understand. We too are temporary, but what we create, stories, discoveries, acts of kindness, travels forward like light. Science and wonder meet perfectly in that thought. The laws of physics may explain how stars form and galaxies grow, but wonder explains why we care. We study the universe not to control it, but to feel at home within it, to trace the lines of connection that run from the first dawn to the present moment. Webb's discoveries do exactly that. They don't distance us from creation. They draw us nearer. Think for a moment about the irony. The deeper we look into space, the more we see that the universe is one continuous act of becoming. The first dawn is not gone. It's still unfolding. The expansion of space carries those ancient photons outward even now, and each time we observe them, we become part of their journey. The universe, it seems, never stopped creating. It only changed the form of its art. There's a quiet reassurance in knowing that. The chaos, the uncertainty, the paradoxes, they're all part of a larger harmony. The galaxies that Webb sees are not older than the Big Bang. They're its lingering glow, still shimmering at the edges of time. Creation didn't end with a bang. It lingers, breathing softly, still expanding, still alive. Perhaps that's why the images from Webb feel so peaceful, even when they're filled with drama. Each one is a window into a moment that has already passed, yet feels immediate. Looking at them, you can almost hear the hush of the early universe, the faint rhythm of starlight spreading through the dark, like waves against a cosmic shore. It's a soundless music, but one that every heart somehow recognizes. And as this story closes, maybe it's worth pausing to remember that all of it, the galaxies, the stars, the telescopes, even the thoughts forming in your mind right now, are made from the same dust that once drifted in those first bursts of light. You are part of the universe's memory, and it is part of you. Every time you learn something new, the cosmos learns a little more about itself. Every act of wonder, every quiet question, continues the conversation that began with that first shimmer of dawn. So tonight, as you drift towards sleep, imagine that ancient sunrise spreading across the newborn universe. Not a sudden blaze, but a gentle illumination, slow and patient. See the fog lifting, the stars appearing, the first galaxies gathering like whispers into song. Feel the warmth of that light still travelling, still reaching, still touching you now. Because in a very real sense, the Big Bang never ended. It is here in every moment, in every breath, in every flicker of thought that asks why. And in that question, that small human spark of curiosity, the universe recognizes itself once more